All right, in this video, I want to have you take down a few notes and draw a few things related to something called reaction kinetics diagrams, or we sometimes hear them called reaction coordinate diagrams. What they are is a sort of profile of the energy of a chemical reaction before, during, and after the reaction takes place. So you should have received a page that has a couple of blank graphs with these x and y axes already labeled and in place. And what I'm going to ask you to do along the way is sort of add in a few labels, a few marks, a few different positions along the graph, and a few definitions as well. The first side will probably take a little bit longer. The back side, once we've got the front underway and done, the back doesn't take nearly as long. So the first one will be a little bit slower as we have a few more definitions to add the first time through, but we don't have to repeat them the second time. So the first thing that you should do here is, excuse me, add in, as you see here, these two sort of levels, these positions on the graph. So here at the very beginning, see, there's a energy stored in the reactants. So it's a higher position. And it doesn't really matter how high you put that, maybe about halfway up on the y-axis. The reactants, the chemicals or the compounds, the substances formed, or present rather, at the beginning of the reaction, have a certain amount of energy stored in them. And at the end of the reaction, the products have a certain amount of energy stored in them. And so that's going to be the label that we'll put over on the right-hand side. And that position should be somewhat lower on this first graph that we'll do. So we're starting at a higher energy position and then ending at a lower energy position, as you see on the graph here. And if you use the dashed lines that are already present on your page, it should be pretty easy to line these things up nice and straight, keep track of how far up and down they are from each other, which we'll use as some labels here later on. So if you've got those positions labeled, the stored energy in the reactants and the stored energy in the products, we'll go ahead and add on to that from there. So I've added here a little arrow that shows the difference in energy between the reactants at the beginning and the products at the end. We'll use a few of these little two-headed arrows to show the difference in position of energy, difference in energy between two different positions on the graph. And so that little line, that little two-headed arrow that we've added in here, represents what we call that change in enthalpy. You might remember hearing about that when we were doing stoichiometry and a little bit of thermochemistry, where we were calculating how much energy a reaction would release or take in using a chemical reaction equation and like a kilojoules to moles ratio for that chemical reaction. We had delta H as our sort of symbol for that, and we referred to it briefly then as what we call the change in enthalpy. And enthalpy is essentially a sort of a scientific word for the energy present at the beginning and at the end of the reaction. So here we're looking at the change in the enthalpy, chemical energy, which is often expressed as heat, between the reactants and products. That's a really important value to label and identify and be able to recognize on any graph, a reaction coordinate graph like this that you'll see in the future. Because we're starting at a higher energy position and ending at a lower energy position, we can see that the energy the change in energy that's taking place in this reaction is a decrease. We start higher and go lower, so that's a decrease in energy. In other words, energy is being released. So we would say that because the reactants have more stored energy than the products, the reaction is releasing energy as it occurs, and we would describe that as being an exothermic reaction. A reaction that releases energy as heat is an exothermic reaction. So put this definition on your graph. I have it up at the top of the page. Maybe put it at the top. I would say maybe if you have room, put it at the bottom. But let's get that description in there. And if you need a little more time to put that definition down, take a moment and pause me here until you have that definition done. And then you can restart the video. I'm going to continue on with the next labeling. So feel free to pause me at any point if you feel like you need more time. The next thing we're going to label here has to do with something called the activation energy. Activation energy is the energy that's required to get a reaction underway, to get the reaction to start. And the activation energy can be abbreviated, as you see here, as E sub A, E subscript A, and that stands for the energy of activation. There are lots of capital E energies throughout science, chemistry, physics, all kinds of places where we use energy. And there's subscripts behind them. The capital A here usually tells you what specific sort of energy we're talking about when we use abbreviations like that capital E. So that's why we see E sub A here, E subscript A, the activation energy. The idea is that once that amount of energy has been added to the particles, you've reached what's called an activated complex. Now that sounds really fancy. It kind of is a pretty important thing, but the activated complex is simply sort of a mashup of the reactants. So if we're combining, in our typical reaction, we imagine combining A plus B to make C plus D, just a real basic reaction template. The activated complex isn't A plus B, A and B. It isn't C and D. It's sort of a moment in between. When A and B and C and D are sort of neither one of them, you're sort of at an in-between, sort of some intermediate stage when the atoms have sort of begun to rearrange into something new, but they could finish and rearrange completely into new products, or they could revert and go right back to the original reactants that they were at the beginning. And so this is sort of a tipping point. It's what we call an intermediate stage of the reaction, because it's in that very small moment between the reactants and the products. And when you're at that intermediate stage, the reaction can continue forward, or it can tip backwards to the original reactants, and you'll have what you started with again. And so we call it sort of a tipping point. That activated complex is an intermediate stage. It's a very unstable and very temporary tipping point in the reaction. I always think of an intermediate here. The activated complex is if I'm shooting a basketball and the basketball sort of in slow motion seems to stop on the rim, and you can't tell if it's going to fall through the basket or if it's going to fall out and not count as a basket at all. And you can't tell. You're at the moment where that ball is sort of positioned there right on top of the rim, and you don't know which way it's going to go. We know it won't stay there because it's not a stable place for the basketball to rest. The rim is far too narrow for the basketball to stay there. So some way or the other, it's going to either fall into the basket or fall out. And so that's kind of what we're looking at here. The reaction can't stay at the intermediate stage. It either has to proceed forward or it has to go backwards, one or the other. So it's a tipping point, sort of like this guy here. He's got his big rock rolled up to the top of the hill. And if he pushes it forward, it'll roll forward and over to the other side of the hill. Or if he doesn't, it might continue. It might roll backwards down to where he started, or even sort of more so than that. We take this kind of guy here. If you were to roll up to the tipping point at the top of that hill, that would sort of represent the activated complex. And this is a really goofy looking hill, but the idea is that this hill, a barrier in between him and the other side, that very small peak is going to be represented on our own graphs as well. So this is sort of a graph that's been drawn in with some pictures and some coloring and whatnot. But before we draw the rest of our curve, what I'd like you to add to your graph page, or to your notes if you prefer to put everything in your notes, is a definition for a catalyst. And we're going to describe a catalyst on our graphs as well. A catalyst is a substance that can be used with a reaction in order to reduce the size of this barrier. So you see here on this graph, or on this picture rather, that he's got a big barrier hill between him and the other side. And to get that rock over it, he has to push it way up to the top of that hill. Well, that barrier is the activation energy, and a catalyst can go in there and actually reduce the size of that hill. So it makes the reaction possible, or more likely at a lower temperature. So less energy is needed than it might be on this on this hill if he was able to sort of find a shortcut through or around, or by sort of lowering the size of that hill. The catalyst reduces the energy required for a reaction to occur, and it makes the reaction happen faster. So on our graphs, we're going to label the activation energy as this peak. So take your pencil there and finish out your curve from the starting point where you had the reactants on the left over here to the products on the right. Okay, so from our reactants here to our products here on the right, I want to draw in some sort of a curve of your own, and you can draw it sort of however you want, but make sure it goes up pretty high, pretty close to the top of the graph, and then it should come down and sort of gently connect in with the products on the other side, smooth out here, and have kind of a flat landing at the other side. And the activation energy then is this tall arrow that I've added in here on the right hand side to represent the amount of activation energy in this reaction without a catalyst. So the activated complex is the tip of that hill that you've drawn in, or that curve that you've drawn in, the activated complex without using a catalyst. And that second tall arrow over here on the right hand side that we've sort of drawn in represents the activation energy of the forward reaction if we aren't using a catalyst. So if I'm following through this curve from left to right, I have to go way up to the top of this hill and add in all that energy just to get to this tipping point where I now have a 50-50 chance of the reaction being successful. And so all that energy from the reactant starting position to the top of the hill is represented by this tall arrow off to the right here. All right, and then down the other side, and we continued out to the products at the bottom end of that hill. However, if we can put a catalyst in place, a catalyst can actually take the size of that activation energy and reduce it significantly. So if I could come up with a second pathway, as I've drawn in here as the darker lower curve, this darker lower curve represents, okay, the pathway or the activation energy that would be available if you had a catalyst. So it's sort of like a shortcut. You still start, and this is really important, you still start here at the same position and you still end down here at the same position, but you found a lower energy requirement pathway to get from there, from on the left side reactants to the right side products. So if you can go through this shorter shortcut, it's going to require a lot less energy, which typically we would see that then as the reaction occurring at a lower temperature. With less energy added at a lower temperature, the reaction still occurs, and so it goes much faster as a result. There would be, we don't have it really labeled here, but there would be at the peak of that new hill then sort of a second activated complex. So we would have a second activated complex here at the peak of that lower pathway, that lower activation energy pathway. So an activated complex at the top of this red curve without a catalyst, and an activated complex's energy at the top of this darker curve if we did use a catalyst. So that's our front side reaction. This is an exothermic reaction, starts with higher amounts of energy and ends up lower, to show that the amount of energy released then by that first arrow that we sort of added in over here on the right hand side to represent that change in enthalpy, delta H. Okay. So on the back of your graph, we're going to go ahead and repeat this sort of idea, but for an endothermic reaction. So there isn't going to be quite as much to say, or certainly not as many definitions, because we can reuse the same definitions again on the back side. Oh, I do have a point. Sorry, I thought I didn't. We do have a point labeled then for that second hill, the activated complex with a catalyst used. So that peak point, again, it's still a 50-50 tipping point, but it's at a much lower energy requirement to get there in the first place. So instead of having to input 250 kilojoules of energy to get to that point, I might only have to input 100. And so it's going to be a lot easier to accomplish that. All right, on the back of your page, if you wouldn't mind flipping it over, we're going to do something very similar on the back. But we're going to kind of do it for an endothermic reaction. So the first position you should draw over here on the left-hand side is the bond energy or amount of energy stored in the reactants. Okay, and then on the right-hand side, we have the energy stored in the products. So a lower position and a higher position, from lower on the left to higher on the right. So it's just kind of a flip-flop of what we had on the other side of the page. And just like before, going from a low energy position to a high energy position, we're going to measure then that as a change in energy. Okay. This reaction is showing that the reactants have stored energy that's less than the products. The reactants have less stored energy the way that we've drawn it here. The reaction is absorbing some energy as it happens, and this reaction would be described as endothermic. So it's just the opposite of what we had in the first one. And we're going to label that as this little arrow that we've drawn here on the left. That little arrow, like on the last graph, represents our enthalpy change. So the difference in energy between reactants and products shows up as a change in enthalpy. And that's still what we recognize as a delta H. And because we're starting lower and going higher, we would measure that as a positive delta H. If you think back to when we were doing stoichiometry calculations with those values, when the value was positive, it meant we had an endothermic reaction. And when delta H was negative, we had an exothermic reaction. So in this case, it would be positive. Starting lower and going higher represents a gain in energy. And so that's a positive delta H value that we'd have there. To connect those, we're going to do what we did on the other graph. Draw a curve that goes up to some relatively high position near the top of the graph, again in this example, and then it comes back down again to connect with the product side of our graph. In this case, our activation energy is this incredibly tall arrow that we've drawn in here. This is a really significant activation energy right across from the reactants to the peak. So that's a ginormous activation energy to get to that activated complex. So that still has the same name. It's an activated complex. The activation energy of what we're calling here the forward reaction from left to right, without a catalyst, means we have to go all the way to the top of that rather high peak. And so that would be a non-catalyzed or uncatalyzed pathway from reactants up through the peak activated complex and then down to products on the right. And in much the same way as with our last one, we can also draw in and show that there's an activation energy if we have a shorter catalyzed pathway through that lower energy input activation energy, as is labeled here. So I've kind of left the first arrow showing here, show the difference between the activation energy there on the left without a catalyst in place is much greater than the activation energy of the forward reaction if we do have a catalyst used. Cuts it down. It can cut it down even lower than that. We could make it so that that little bump at the top of the hill is practically nothing, so that the activation energy would be far less significant overall. All right? And again, the second hill has a peak, and that's that 50-50 tipping point for the catalyzed reaction. So that's the activated complex with a catalyst being used. So hopefully these two graphs, right, show a really similar sort of set of ideas, but yet show some opposites as well. One endothermic on this side, the first one we did was exothermic, this one's endothermic, and that the activation energies and the delta H enthalpy values, those are pretty similar in terms of how you find them from reactants to products. And notice a really important thing here that the activation, or rather the catalyst doesn't do. The catalyst does reduce the activation energy. It makes that energy barrier much, much smaller. What it does not change are the positions of the reactant energy and the product energy. The graph still begins in the same place and ends in the same place, even if we do use a catalyst. The delta H value, that change in energy, here shown as the very far left arrow over here on the left-hand side, that change in energy from reactants up to products doesn't change if I use the catalyst pathway or the not catalyst pathway. So that's important to notice as well, that all the catalyst is able to do is reduce the barrier. It doesn't make it endothermic when it wasn't or exothermic when it wasn't. That part of it doesn't change. All right, and that's all we've got, I think, for our notes here. So wrap up with that, and we'll follow up with some questions where we'll have you draw some curves like these and actually put some numbers on that y-axis especially, so that we aren't just working with arrows. We're actually able to make some quantitative measurements and have you do some subtractions in those examples to understand how to read a graph like this and how to draw one based on descriptions of reactions and the energy that goes with them. We'll see you then.